Okay. All right. So there's something else, but I forgot. Okay. Well, I can do whatever you want, or I can go and look on the. I have the thing open, the thing he sent with all the topics.
Mm-hmm.
So I could just do that.
That'd
So
be
yeah, okay.
That'd be
The,
wonderful.
the other thing though is that like the first one is like understand linear and curvilinear kinematics, position, velocity, acceleration. I don't. Would do you want me to like
Maybe just
talk
like
about the concepts or like do a problem or?
maybe like the main like equations we need to
Sure. Yeah.
know,
Yeah.
and then like an example problem.
Sure. Sure. Okay. Um. Yeah. Okay. So yeah, I would say for the this is probably what I should. Right. So there's linear and I'll say rotational. He says curvilinear, which is sort of an I think it's a word, but I don't really like it. So there's position, velocity, acceleration. Right. I'm not going to write the names. These are and then I'll write the rotational versions, theta, omega, and alpha, and these are just well, okay, so I really should say these are all 6 of these are vectors. This was now a displacement, right? So it's not a, you could call it position depending on your if you're doing a one-dimensional problem, you don't really care about the fact that they're vectors. That just means they have a sign, which most of the equations, I'll write in a second, but those are for one-dimensional problems. So you don't normally have to worry about the fact they're vectors, but you should know that they are vectors, in which case this is the actual displacement, and this theta is the angular displacement, it's called, which you might think, well, the fact that it's called theta is very suggestive of the fact that it's just an angle, right? But of course, the fact that it's a vector means that it could be either, if it's minus, then that's a minus angle, right? Okay, so that's this, and then to get from here to here, from this line to this line, we can take a time derivative. All right, same thing over here. There's nothing special about the rotation part. It's just still a time derivative to get to here. Now, you don't usually have to explicitly do the time derivative, but that's, what this means. In other words, you could write this as delta over delta t kind of thing. Like delta x over delta t is the velocity for an average velocity. And then again, you could do the same thing here. ddt to get to a. That's the same thing here. So if they gave you, I guess, an explicit function like x, the position of something was given by like t cubed, right, alpha, beta times t cubed. Beta is just some constant. T cubed is like, so in other words, at time 0, it's at position 0, and at time 1, it's at position 1, and at time 2, it's at position 8, right? If it's given by this, note that you need a constant here because otherwise the units don't work, right? So this has units of meters per second cubed, apparently. Anyway, then you could get v by just taking the time derivative of this, which would be 3t squared, right? Times beta still. And then you could find the acceleration of this by taking 6t times beta, the derivative of that, right? So if they want you to find it, I don't know how often. I mean, in physics classes, they would ask you to do things like this. I don't know really if they'll care about this, especially because there's only 3 questions, I think. So I doubt this will be one of the questions, but this is how you and this is always true, of course. None of these are going to be like specific to the question. These are all always true. And the same thing would happen if you put theta and omega and alpha here. So that's that. So all right. So now I'm going to write the sort of equations of motion or whatever you call them, or kinematics equations, I guess I would call them. These are one-dimensional equations, but remember that in the first class, I think he wrote them as vectors. They just become 3 separate equations for each dimension. So most of these types of problems you will only just do in 1 dimension, but if it has 2 dimensions, you of course, you know that from the project or from all that stuff, that you have to break it into the 2 components. And they're just separate, unless, of course, you have something that mixes the 2, like their drag force, remember, had a v squared, and v squared, of course, depends on both. You could write it as like vx squared plus vy squared. So anyway, it's normally, though, you would have, let me write, x is x naught. So I'm going to write x meaning, it's really, you could write it as x final if you want, but x naught plus v naught t plus 1/2 at squared, right? And so of course you could write this in different forms. You could move this over and put delta x, meaning like the change in x from 0, or you could adjust your starting position to be 0. Those mean the same thing, of course. You know, you could set your system up like a falling object or whatever so that v naught is 0. That's a nice thing to do. In the x direction, so I've written it with x here, but normally when we deal with x and y, in the x direction, there is no acceleration, right? Of course, if there's drag, that's different. But if we're just talking about a projectile with no air resistance, the ax would be 0 usually. I shouldn't really write this. It's not really true in general or anything. It's just usually. And ay is usually minus g. Okay, and remember that, of course, if you set your system up so that you're calling upwards positive displacements, so if the final position, which is here, so if the initial position is some height and the final position is 0, then your displacement actually went down. That's fine, and you have to make sure which is negative, and that's case you'd have to have minus g here because you were calling upward positive because your final position was. You called your initial position higher than your final position. So of course you could reverse everything and make, you could sort of start counting distance downward if you want. That's a little confusing. And so anyway, just the signs have to match basically. All these. And the other one is kind of the only other one that you'll ever use. This comes from, well, I think you can get it from kinematics and stuff. You can also see it more directly from conservation of energy. Because if you just multiply everything by 1/2 m, multiply everything by 1/2 m, you'll get 1/2 mg squared, which is kinetic energy final, is the initial kinetic energy, which might be 0 sometimes, and then this will become mgh, right, which will be the potential energy. So that means the same as this. Of course, if they give you a problem where you just need these, they will call it a kinematics problem because they won't call it an energy problem usually. But I mean, you can call it whatever you want. They're all energy's conserved, so it's fine. But anyway, so that's that. So I think that's pretty much it. I mean, also I guess you could list if you wanted to list more equations. You could always put like v is delta x delta t, right? That's like fine. But of course, you don't really use it very often, and also this is true only when, this is only true this is giving you the average velocity, right? So if you have some acceleration, this won't be true in general. It'll be true to give you the average velocity, but it won't be true to give you the instantaneous velocity. To get the instantaneous velocity, you need to literally take the derivative of x. Take the t and plug in your time, right? T equals t naught or whatever it was. That was just what I erased before. It's just taking a derivative. So that would be to get the instantaneous velocity. If they ask you about the average velocity, it was the same. Remember the problem with you walk like this far and then this far and then this far and then this far. It wasn't two-dimensional, but it was like they gave you a graph and they said if you walk this way and then back this way, what's your net displacement? The net displacement is 0, and therefore if they say what's the average velocity, the answer would be 0. If they said what's the average speed, you would have to compute the speed here, and then compute the speed here. And speed is always a positive number. Like speed is like the sort of absolute value of the velocity. So then you'd be this, and if they're the same slope but negative, it would be the same speed here and here. Anyway, so yeah. Okay, and then same as this, you could get the average acceleration, which would be delta v or delta t. That's okay. The instantaneous acceleration, of course, would be the derivative of v respect to t. Anyway, so basically, these are the two kinematics equations you'll use. These are true for one dimension. You just have to write another copy of them if you want to do it in a two-dimensional problem, which like projectile problems where they ask you, there's a cliff and then something was either launched off the cliff this way or like went in the air with like a cannon, right? And you need to find how far it went. Let's just do that one. because that's a good example. Now, if they ask you things about, I'm not going to do like what angle it fell at. If you wanted to do that, we would need to, well, I'll tell you how to do it. I don't want to it's just going to be a lot of algebra that's not very interesting. But, yeah. Okay, so let's, I'm going to erase this down here part. So let's say it launch at an angle theta. Of course, as usual, I'm not using any numbers because then that's boring and you can't see anything. And we're not going to say anything about, and it's launched at velocity v naught. That's the sort of the velocity it's launched at. That's not the components, right? And I'm not going to say anything about the height and stuff because that's not given to us. We could determine it if we want. We don't want to determine it in this problem. I'll just say we want to determine this. Of course, you could get all that information if you wanted, but let's just pick one thing, which is this range, they call it sometimes, the range. I think he said something that there's like a range equation. I don't know. I don't know what that is. It's just what I'm going to do right now. You could get it from this. It's there's no point in memorizing more than you need to. Okay, so let's talk about the two components. So so if this is v naught and this is an angle theta, what are my two components of velocity? Those are very important because we're going to have to do one of these equations or some set of these for x and some set of them for y. So this is going to be v naught sine theta. You can tell it's sine because, like, when you break down a vector like this into two components like this and this of course is going to go here, but like you can always move vectors around to add them. You add them. I think this might have been on that little quiz thing that you took twice. That to add vectors, you put the tail of one next to the tip of the other, something like that. Anyway, that's true, but it's sort of a weird way of saying it. But anyway, and so the resultant vector, the sum, goes from the beginning of one to the end of the other. So if you add a bunch of if you added a bunch of vectors like this, you would have to like stack them like that, and you get the resultant vector. Anyway, it's a little hat. Anyway, okay. So the point is that you can see that it's sine because it's opposite over hypotenuse, right? Just do some trigonometry. Sine equals opposite over hypotenuse. Move the hypotenuse over, etc. Then of course this has to be cosine theta. Now I know that because it's the adjacent side, or I could figure it out. You wouldn't do it this way, but you could figure it out by the Pythagorean theorem and sine squared plus something squared has to be. Anyway, of course you're never going to do it, but that's kind of a fun thing to do. You could let me say it actually a better way that makes more sense, which is to verify it. You could say, well, it's a right triangle, so a squared plus b squared equals c squared, and of course sine squared plus cosine squared is 1. You can factor out the v naught squared and take the square root. Anyway, okay, so these are the two components, and so let's write the x direction here and the y direction here. So I'll do the x first. So what are the forces in the x direction? Well, there's none, right? We have an initial x velocity, so I'll write x equals, and actually I can kind of do the whole thing in one step because there isn't like any complicated, like I said, there's no forces in the x direction, right? So whatever my x velocity is, which is v naught cosine theta times t, right? No forces means there's no acceleration, basically. So I'm using this equation here, and where ax is 0. So x is, and I'm calling this x equals 0, so that's 0. And then v naught is this. And of course, this v naught means initial velocity. In the books and stuff, they'll write x's next to all these things. I'm just not going to confuse it, but we know that this means this whole thing has to be in the same direction, right? So this is your v naught. T is here. This term, as we said, a is 0, and we said that x naught we just defined to be 0 because we only want this distance anyway. So that's it. And now, literally, we're done, except we need t. Now, how do we find t in the x direction? Well, we have no idea because what happens here in the x direction? Well, nothing. Like if the ground wasn't here, it would just keep going. So how do we know what t is? T is the total time, of course, right? Because it was traveling at this velocity for the total time. So to find t, we would actually need to use the y direction to find when it lands, because that's the condition of when it stops going forward. Of course, if the ground, as I said, if the ground wasn't here, it would just keep going in the x direction too. So we need to find this t. So actually, when you see like a problem, if they ask you only something about the x direction, you should and you shouldn't write things about the y first. I mean, you might because you know what to do. But if you just didn't know anything about what you needed to do, you should be like, well, let me just literally write what I need to find. It's x. How do I, and just plug in this equation for x. So what do I need now? T. And now it's a little more clear of, you don't have to be like if you just go and just find all the things, like if we found the height, like I said, like in the other homework problems, I was finding the height and stuff like that. That's fine, but in this case, we actually don't even need to. You should this is like a problem solving tip, I guess, is try to literally do it, the final answer as soon as you can, and then see what you need to do. Now we found it, and this turns into a t problem. So now when we do the y direction, which is what we need, we only need to, once we find t, we're done. We can plug it in, right? We don't need to do anything special with the heights and stuff like that. So now let's do the y direction, and we'll see. Let's just do it all in one step. Now we could do it the way I was doing it in a month ago, whatever, right? When all those problems, it was a little easier because it was sort of symmetric in a lot of those things. We could do 2 sets of something falling, right? Now we could do that. It wouldn't be that hard. We would need to find the height in that case, which we could do. Again, it's not going to be crazy hard, but let's just do it all in one step, because if we keep our signs right in the y direction, we should be all good, right? So we're going to call this to be this positive. Of course, we implicitly assumed that this was positive in the x direction. We're going to say this is positive in the y direction. We could choose all possibilities of this. It doesn't have to, this could be down and this could be left, doesn't matter. And so now we're going to say, well, we're going to use this equation, y. Now, y final, we want to be what? Oh, sorry, I had to tell you the height of the cliff. I forgot about that. That's very important. So the y final, we'll call this 0, okay? And we'll call this h. So y, the final position is 0. What's the initial position? That's what this is. Well, it's plus h. And remember, I could have also called this 0 and this minus h, and you can kind of see how that's equivalent. You can just move the h over. It's the same thing. And we have some initial y velocity, which is v naught sine theta. Sorry, it's going to be messy because I'm running out of room. Plus, well, now it's going to be, of course, the acceleration is just g, and it's going to be minus because this was plus because it was going up, and now this is minus because it's going down. There we go. So this is, sorry, looks a little messy, but this is a t. So it's just this equation, v naught is v sine theta, t. A is minus g, so there you go. And, well, that's it. And now what's the only unknown here? This is given to us. Theta and v are given to us. H is given to us. G is known. So we just need to solve for t. And so now we can just solve this for t. And now we have to use the quadratic formula. So it's going to be a little annoying. But if it already is in the right form, I guess, right? Well, let's just divide everything by minus 1/2 g to make the coefficient on the biggest term 1. So it's t squared minus 2, I'm going to screw this up, v naught sine theta over g. I'll check this in a second. Minus 2h over g. I shouldn't have done all those things at once. So we multiplied everything by minus 2g. No, we multiplied everything by minus 2 over g. Okay, maybe you should do this in more steps. Or, I mean, you don't even have to do this. You could just plug in, the quadratic formula has a term, this is a, right, in the square root of whatever it's called. So you could just do it. I just don't really like doing that. So I'm going to assume this is right for now. There may be a mistake on video for everyone to see forever. But anyway, so now we can use the quadratic formula. We get t is minus b, which is this one. So it's going to be 2v naught sine theta. The answer, I guess I'll write it, but it's not going to look nice or anything. If you had numbers, of course, I guess now is a good time to plug them in. This squared, so it's going to be 4v naught squared sine squared theta over g squared minus 4a 2h, whoa. Okay. I'm not a big fan of this.
What happened with time on the second term?
Oh, sorry. Yeah, this is a t. Yeah, you're right. Yeah, so I did use that here. That b was the coefficient of
Right.
the single t thing. So I don't know. This is something. The thing. Okay, let me tell you. The thing that bothers me is that there's an 8 here, which I don't really like, because then the 2 is going to cancel. So we can cancel the 2's like this. That's 2 squared, and this cancels. But now we still have a 2. Oh, because we can probably relate. No, we can't relate h. Anyway, okay. So you get something. If you had numbers, you would plug this in, and you would get t is. Now you would get 2 answers. You would get. I'll call it. I'll make up answers. 1.5 seconds and 3.4 seconds. Let's say you get this as your answers. They don't have seconds. I mean, you know that they're in seconds because of everything. But so now this tells you when. Oh, sorry. I'll say minus. This is what you get, and the reason is because, of course, this equation doesn't know anything about the fact that time goes forward, right? It just gives you the answers, and of course, the height is going to be 0 back in time at this point. So you're going to get a negative answer, and you're going to get some positive answer. And you know, of course, just you have to pick the positive answer because that's the answer. Yeah, we don't like if you, for example, if it was just flat, like if you just wanted to find when it was like landing here, it's always going to give you a 0 right away because at the beginning it was 0, and then at a later time it's again 0. But anyway, so you get some answer, and then once we have t, this is the time that it's here, right? The time that this projectile starting here is here, and now we can just plug that in to get x, which is the range. So, yeah. I guess this is fine. It looks a little weird, but I guess it's fine. So it's very hard. It's not going to give us anything nice algebraically. Because these could, like, h does not depend on, like, v naught and h are completely separate, so I guess it makes sense that they're separate in the equation. They don't cancel or give anything nice here. Maybe they do if you play with it a little bit, but that's boring. So anyway, does that make sense? This is one example. Of course, this is kind of the hardest example. Now, also I should mention, if they want you to find the angle that it lands at, let's say, so it lands, let's say, at this angle, they want you to find this. I used theta already. Phi. How would we do that? Well, I'm not going to. I won't write all this stuff because it's just not very interesting. But it's basically just going to be the end vector. The end vector that we care about with the angle is going to be the velocity vector. The velocity vector is made of components. All right, I will write something. The velocity vector is made of components, downward, right? So this is the angle we want here. And notice that the horizontal component of the vector is, of course, just going to be v naught cosine theta. That's the horizontal velocity the whole time. The vertical component, though, is, we don't know. We have to figure it out. And that way, we would have to actually solve for the final vertical velocity of this thing. So we would have to use, like, this formula, right? Yeah. So anyway, and then once we have those two components, of course, we could do some kind of arctan or whatever it's called, right? Yeah, arctan, I guess, of y over x kind of thing. Okay. Or if we want to find the speed it lands at, that would be another thing. Maybe they'll ask you the angle and the speed. Well, of course, if we have the two components, we can just take the square root of the squares of them, sum together, kind of thing. So, does that make sense? Okay. I don't want to take too long on any one thing because I want to get to everything. I'm saying that like it's not my fault. Okay, understand and be able to apply Newton's laws of motion, and then the next one is be able to draw free body diagrams. Yeah. So, okay, so I'll say, so I don't want to spend too long on any one thing, especially if it's one thing that we don't really need to practice a lot. Like, free body diagrams, I'll go over one, but once you know how to do one, you kind of know how to do it. So, what was the one I just skipped to? Oh, Newton's laws of motion. Yeah, so, okay, I'll just say Newton's laws of motion, and then I'll say free body diagrams are kind of related, right? The first, well, if you use this, so this is, of course, Newton's second law. This is the sum of the forces. It really should be, I mean, when they say F equals ma, they really mean like the net force, right? Or you could also say the sum of the forces, the same thing. So this is just proportional exactly to its acceleration. Yeah, and when a is 0, so when a is 0, that means that v is constant, right? These are the same statement. Constant. Now, constant means a constant positive, negative, or 0 speed. That's fine. And therefore, this says that when there's no forces, so this and this say that when the sum of the forces on an object is 0, then it has to move at a constant speed, or whatever speed it had, or 0 speed of it. So that implies the first law, which is what I just said. And then the third law would be, yeah, if you have, so the third law I would say, if you have two objects in contact with each other, well, no, I'll say if you have two objects exerting a force on each other, then the force one exerts on the other is equal to the force the other exerts on the one. That's not a good way to say it. The force A exerts on B is the same as the force B exerts on A. Now, of course, this is the part where it's very confusing, because when things are exerting forces and also touching, you might be sort of thinking, oh, well, maybe there's some kind of dual forces between them or sort of. Most forces that we care about are, well, that's not true. Like gravity, which is what sort of the main one we look at when we do projectiles and stuff. Gravity is exerted by the Earth. So the dual force is exerted on the Earth, but we don't normally draw free body diagrams for the Earth. So not every force you'll draw in a free body diagram has a dual force somewhere else. It only happens first of all, it really does happen for every force in the universe. But when we only draw the free body diagrams for two objects, they only exert forces on each other that are dual in the forces they get by contacting each other, basically. And the ones he was, I hate to bring this up again because I think it confuses everyone, but when he listed the sources of force, there's just like gravity, electromagnetism, and then the nuclear forces. So there's no nuclear forces here, don't worry. But gravity and electromagnetism are like the two things that forces can come from. That's literally that we know of. That's all that we know of. So if you're thinking about what's exerting the force on the other thing, you should really think about what's actually exerting this force. Is it sort of electrons and surfaces pushing each other, or is it gravity? That's all it can be. Or it can be electrons doing other things or whatever, right? But that's how you can figure out the dual force. So if you have like a block sitting on a table, let's say sitting on another block, and you're saying, okay, well, the top block here, I'll call this A and this B, even though I just called this A and B. Because I don't want to do that one because that was on the homework. But so A has what? Well, it has a force of gravity on it. We know that it we know that it's not accelerating downward, so it must have some force up, and I'll say it's the normal force, but it's exerted by B, so we can call it F of B. And now we immediately know that when we draw B, well, of course it has gravity, but it also must have the exact opposite of this force, B, because if B is exerting, this force is exerted by B on A, and so therefore it must exert an equal and opposite force like this, right, downward, because it's opposite of this, Now, of course, now there's extra force downward, so of course there must be some force up, which is going to be the normal force from the table. I guess. Now, you'll notice that this is higher than it would be if we didn't have A on top, which literally is just saying that it's heavier if you put things on it. Like it's not a deep statement. It's just saying, I mean, you might sort of like, how is B heavier when you put something on top? Even if you treat them as separate objects. If you treat them as one object, you would just say, well, it's bigger now, so there's more gravity. But this force of gravity here doesn't include A at all, right? The reason it's sort of heavier, if you feel something, if I feel this and then another thing on top of it or whatever, right? The reason it feels heavier, I could consider it as, oh, it's all one object and it has more gravity. That's valid. You could say that. But we could also say that the thing on top is having gravity on the thing right below it. That thing must exert a force upward to keep it from going through the object. And therefore, their equal and opposite force pushes back down onto my hand. Right? Well, it pushes onto this object, and therefore the normal force my hand has to apply to keep it up is more because there's gravity, its own gravity plus the normal force from the second part. So those, you can consider things as two separate objects or connected, and of course you should get the same answers because it shouldn't depend on, every object is sort of, you can cut it, right? Why should it be different if you cut it in half, right? And so this is like FB dual, I'll say. I'm supposed to say dual. Anyway, it just means it's this force, but it's imposed down on here, and it's not the gravity from this, because the Earth gravity, using gravity to act on this doesn't affect B at all. B doesn't care at all about the gravity on A. So the reason it feels more weight is because, the reason you feel more weight is because the dual force to the force it's holding up. Yeah.
FB is related to the weight, right? Because it's equal to FG.
Right? FB is related to the weight of FG of A. Sorry.
Exactly.
Yeah, you're right. Yes, sorry. So this is related to gravity. Yeah. I shouldn't have said that exactly. This is related to gravity of this object. Okay, does that make sense? So that's okay. Do you have any questions about this?
In the assignment we have from the book, there's a free body diagram that it's kind of tricky because everything is in an angle. You know what I mean? I know it's reactive forces. I call it like
sure.
Reactive force. It's easy for me to see when everything is horizontal.
Yeah.
But this really confused me because it's a rod and it's in an angle.
Yeah.
That's receiving attention. So my doubt is it's not moving, right? So the reactive force is what direction is going to have? I have no idea.
The one you mean with the rod and there's a rope here, or whatever?
Yeah, exactly. There's a tension.
Yeah.
And I think there's gravity also. But
yeah, sure.
How do you know the direction of the reactive force you have in the joint points?
Yeah, well, so for this one, I hate this problem, by the way. This is a really annoying because it sort of doesn't make any sense as a whole thing. But I would say that that there must be some component vertically from T. Now, if it's in 3D, of course, it's really complicated. But there's some vertical downward component from T. There's some downward component from mg. There must be some upward component here because otherwise it would go down, right? Forget about rotation, all that stuff. That's also true. But for rotating systems, they still obey this too. This is true for, so this is not, it's not like this is true for linear and the other one's true for, this is true for every system, right? So even for this one, even though it's in the torque chapter, that doesn't mean that it's still, you have to take the sum of the forces in the y direction just for, or the z, I guess you would say. And there must be some force here that is equal to mg plus the z component of t, I'll say. I'm saying z because it's like three-dimensional, but it must be, I guess you would say minus or whatever. Anyway, I'm not going to put the sign, but you know what I mean. It must be this because it's not going down. Now, this is just the z component of f. It must also have other, like if you take the x component, let's say this is x.
Okay, I got it.
Then it must have some other component right here.
So there's a summation that will give you
so
the final direction, I guess.
exactly. Now, the question there was asking about torque and all this nonsense that is impossible to solve, I think. But the point is that you can find a lot of information just by using, like when you see pulleys and stuff, you'll probably think some of the torques is I alpha, which is what I'll do in like a few minutes. But of course, it's still true that some of the forces has to be the NA, right? And so you can, if it's in 3 dimensions, if it's in, let's say it's 2 dimensions, just to make it easier. If it's in 2 dimensions, you actually have 2 equations for this because you could decouple them into, fx is max and fy is may, right? Or equivalently, things that are not moving, the sum of the forces in the x direction is 0, sum of the forces in the y direction is 0, z direction 0. So regardless of what you say about the torques and it must have a lever, sure, fine. But it also is not moving. So, it's not accelerating. So this is definitely true no matter what silly thing is happening here. Yeah, often you'll need to, like actually we saw in class the other day that, or yesterday I guess, that when you do the pulley thing with the 2 blocks, you do need to use the forces on, you need to use the forces on the blocks as force things so they're not rotating. You could often also use the force on the pulley, not the torque, but the force on the pulley. It's usually not very interesting because if the pulley is just being held up by like a string or whatever, there's just like a normal force. So it's not, you can't really, if you don't know the normal force, which you often don't, you can't really conclude anything because that's like an extra unknown. So you wouldn't normally include that, but it's always true. So you might as well try it. Okay. So that's free body diagrams. Newton's laws. Conservation of energy and momentum. Does anyone want me to talk about this more? Okay, so the next one says conservation of energy and momentum. I'm going to say linear. I'm going to say angular momentum too, because why not? Okay, so I'll say if. So this implies. This means implies, by the way. If A is 0, means if it's not moving, then sum of F, I'll say X, is 0. Actually, I should say I. When I put I is called an index. You probably know this, but called an index, and I can be either X, Y, or Z. And the fact that I put the same one means the same one. Just anyway. It also makes this, it actually says skip tensors, but I'll just say, this is the last time I'll say tensors, but this is actually called a tensor, like a 1-index tensor. You could put more indices and then it would be more complicated, but anyway, the reason I'm using an I is because I don't want to write X and then say it's true for Y and Z all the time because that's what this I means. Anyway, so this statement follows from this. So if there's no acceleration, if it's constant velocity, you're not moving, the sum of forces is 0, but it also implies that if the sum of the forces is 0, then, and now of course we could just say then A is 0, but let's just say something a little more less obvious than this, which is that if the sum of forces is 0, then P is conserved, where P is just mv, right? The mass times the velocity. Now of course, if F is 0, then A is 0, which means that V is constant. But I'm going to put an M there too. Now, the reason is because this technically kind of encompasses a bigger sort of set of things. Because if you imagine 2 like balls hitting each other and bouncing off, right? In this total system, there is going to be forces that if they bounce off, there has to be some forces, right? Because one of them is changing direction. That already you know there's forces. But in the entire system, is there any external forces? Probably not. Well, how about, no, there isn't. I promise there's not. I'm telling you, they have to tell you there's not. But there's no external forces, and therefore the sum of the total momentum of this system, so this doesn't have to be one object. This could be multiple objects. then this is the total momentum before, and the total momentum after must be conserved because no external forces were involved. So if we asked you, let's say, so let's just do this. Well, yeah, okay. It's not. I'll set it up. I'm not gonna do it because it's not interesting. But let's say you have two little pool balls or whatever, right? That's a good example because they're designed to collide sort of elastically. That's the reason, I guess. Elastically meaning that they completely separate and that energy is conserved. That's another thing. So let's say they go like this, and they go like this, and okay, let's say this has M1 and M2, and this is down here M2. It's the same. Sorry, I didn't mean to write it different. It's the same one, right? So M1, M2, and they come in at V1, V2, theta, phi. I know there's like way too many things already. And this has some V1 prime, V2 prime. I'm setting up to the most general. I hope it's not just confusing with all the angles and stuff, but I'll call this theta prime and phi prime. Okay, so yeah, yikes. It's really not that hard though. It looks much more ridiculous than it's all we know. So let's say they said they give you M1, M2, they give you V1, V2, they give you the angles, and they say, I don't know I guess, okay, maybe they give you one other thing. It doesn't really matter. But let's say they say what angle do they leave at or whatever, right? The equations that we use to solve this, and I'm not going to plug everything in, but the equations we use to solve this is momentum in the x direction is conserved, and the momentum in the y direction is conserved. It's because it's a vector. We could write it as px, py, pz equals m v x. We could basically separate it into components. And so we get that px before equals px after, right? And py before is py after. But let's I'll just do px before a little bit here. So of course px before is going to be the total momentum this is the x direction before, okay? Actually, sorry, let me just do y. I mean, of course you'd have to do both. I just want to set one up that's going to sort of be nice to set up. What's the total y momentum before? Well, it's going to be v1. So the first piece is the momentum from this one, which is going to be v1 sine theta, right? It's this component. It's the y momentum. So m1 times v1 sine theta, right? Plus, but of course, because it's actually this should be minus because it's going downward. So the reason I want to do y is to show you that if we set them to be equal, if we set the masses and the velocities and the angles to be equal, there should be no momentum in the y direction, right? Each one has momentum, but they should have exact opposite momenta, and you see that because there's a minus here. And the other one is going to be plus m2 v2 sine phi. Okay, so that's the total momentum before. And then after, well, it's identical. It's going to be exactly the same, but of course I'm going to use these two. So everything's the same. It's just I add primes, I guess. So then, well, except of course this is going to be positive now. So m1 v1 prime sine theta prime plus m2 minus, because it's going down now, to v2 prime sine v prime. So, okay, so this is messy and a little hard to see what's happening. Really all I was doing was saying that I'll take for every object that's moving, I'm going to take the y component of the velocity, and m times that y component of the velocity is the y momentum. And this is before, and this is after. And so I just take the sum of all the momenta with, of course, it's a vector sum. So, right, so of course that means vector sum when one dimension, that's a sigma. It's a little silly. The vector sum in one dimension just means make sure the signs are right. That's all it means, right? It also means break it down into components, but and so these must be equal. They don't have to be equal. We have to add them together, and then we set them equal after. So now this equation has many unknowns, and they might give you some, and you could plug in numbers. That's fine. but you won't be able to solve anything with just this because you'll also need to set up for the x total x momentum before equals the total momentum x after, which just means that the total momentum in this direction before is the same after, meaning maybe they'll transfer some from one to the other, that's fine, but it won't change overall. If it does change, that means that there's some force acting on it, right? So I could write that, it would kind of look like this with cosines, but whatever. Also, everything would be positive because everything's going in the same direction. So then we have, I'll just write px before equals px after. So conservation of momentum is always true. Don't worry about the collision, all that stuff. And as long as you take into account everything that's colliding, which is these two objects, these two equations are always true. So I'll sort of box them. It doesn't have to be two-dimensional. You can do a one-dimensional collision. That's fine. It's even easier because you just need one.
It's not conserved if you have like friction, for example, right? Then you dismiss that breaks.
Well, yeah, because if you have friction, then the sum of the forces is not zero, and so yes, you're right. Then it's not conserved. Okay. I mean, I wouldn't call that a collision then.
Okay.
Well, okay, you could collide things, but if you had friction, you would want to consider. Well, you won't have a problem with that. Basically, I was going to say you should consider the velocity right before the collision. So don't worry about the energy lost outside of it. But in that moment, this is still true. So, but anyway, that's not if you have a problem like this, it'll just be literally like this kind of thing, or maybe even a one-dimensional version where you just have an object with another velocity. They hit each other and then they bounce off each other and they keep going or whatever. So, which is just one of these. And then of course, these are not going to be enough pieces of information. So we also have to use the fact that because this is an elastic collision, the kinetic energy is conserved too. Okay, kinetic energy, remember, has v squared in it, so you cannot break it into components. It's a scalar number. Kinetic energy is a scalar, so there's no components of that. There's just one Ke before, which is the sum of these two kinetic energies equals the sum after. So with these three, you should have enough information because that's the only things you know about. Yeah. The other situation would be an inelastic collision, which would look like this. It would have two things colliding, and let's say these stick together. Well, let me draw it like that, and then they go. So they're glued together, okay? This is identical, and they don't necessarily go in a straight line. Let's say they go like this. That could happen, of course, if one's heavier or one's going faster, whatever. So in that case, we can't use this equation here because while, of course, the total energy is conserved, some energy, this is actually like the thing with the thing that deforms your head or whatever.
The apple.
Yeah, the apple and then the steel ball or whatever. So we could compute the work it takes for these to stick together. Even if it doesn't deform anything, there's some energy it took for the glue or Velcro, whatever, however you got them to stick together, some energy went into that, and we're not capturing it with kinetic energy. So kinetic energy, or another way, I think the way they say it in the book is it's either kinematic energy or there's a word they use. I can't think of the word they use. But anyway, it's maybe kinematic energy is not conserved. Meaning the energy is still conserved, but it went into something that's not kinetic or potential. Can't remember. Anyway, so we basically just say we're not going to use it. And so without using it, you might think, well, then we can't really solve the problem because I said you don't have information before. But if we have this situation, we only have 3 total objects. We have 2 before and 1 after. So actually, we do have enough information if we choose momentum. Momentum is, of course, still conserved, even if there's forces internally. And the reason, actually, one of the reasons we know it's conserved is because even if these exert forces on each other to keep them together, because of Newton's third law, the force they exert on each other are equal, and so in the total system, they cancel out. I know you're not supposed to say Newton's third law makes things cancel out, but they don't cancel out in each individual object, but when they're glued together, in the total system, if we just put this in a box, there were forces, but there's no external forces. So if we add up all the forces on this combined object, they do cancel because they act on each other. So in other words, momentum is still conserved in this inelastic collision, but the kinematic energy or energy of motion, or whatever we call it, is not conserved, so we wouldn't use that.
It's mechanical.
Mechanical energy, that's what it is, yes. Thank you.
Mm-hmm.
So mechanical energy is not conserved in inelastic collisions. Collisions where things stick together. The other common one you would do, I won't do this example, but it's just like a bullet fires into a block, which is not moving, and then the block like swings up at some angle, and you have to find the angle based on the initial, right? So this we could of course use momentum initially, which is 0, if this was stationary, plus the momentum of the bullet, is the total, here is the momentum after, but now we have the masses, sort of, we have to sum the masses together. We get some velocity, but of course we could also just convert this immediately to potential energy to get the total height, and then do some triangles and stuff, you can get to the thing. So anyway, that's how you do that thing. We wouldn't need energy at all in that case because, well, sorry. We might need energy to convert it to potential, but it's not that the energy of the bullet equals the energy up here. You'd have to convert it by momentum to find the velocity, the initial velocity once they collide, once they start swinging. Then you could use energy to, so it'd be like a two-step problem. You'd use momentum to go from here to this combined system. Then now that it's a combined system, energy is of course conserved because nothing else is colliding anymore. So it's just a single object swinging, converting kinetic to potential. Okay. Yeah. Oh, and then so we know the work energy theorem too would just be, they wouldn't ask you for this, but it's just sort of energy gets converted into something that looks like this. So work is this, and this has units, it's kind of like energy, meaning energy can get converted to this. So this is like friction. So I won't do it again because it's in, I think it's on video somewhere, right, on YouTube. The thing with the block that slides down, and there's some friction here, and you have to find how far it went before it stops due to friction. Anyway, I'll say it real quick. It's all the potential energy here, which is like mgh, and you'd have to figure out what h is exactly, but all the potential energy is going to get converted to something like this, for friction times the distance it went, and you could solve for the distance. So this is the work energy theorem basically, is that work is F times d. It's really a dot product, it's really an integral and all that stuff, but generally it just means, you know, the distance you go in the same parallel to the work, or sorry, parallel to the force that's being applied. That force will give you some energy or cost you some energy basically. Okay, so then, does anyone have any other quick? So then now, okay, I'll erase this in a second, and then just talk about rotational stuff, because that's probably the thing that you need to see the most, because you've seen that for like, I guess 1 week now, 7 full days, I guess, or 8 days. Okay, does anyone have any questions about other things besides that first, before I do that? All right, so I'll start with just some of the torques, because it looks very similar to what's already here, which is, oh, I shouldn't have, I actually meant to leave that up, because if we kind of convert it to an angular form, we get this. The sum of the torques is equal to I alpha. Now, I is always going to be a number here, because he said ignore tensors. There are situations where I is a little more complicated, and this becomes a sort of complicated product. They're always going to be numbers here, and you're basically going to look it up on the table, or do the parallel axis theorem, which we'll do an example of in 1 minute. I'll draw this so I don't forget the example I was thinking of. Okay, so just like F equals ma, torque is I alpha, right? I is just like m is sort of the resistance to a force causing something to move, right? This is the resistance of something turning. If you apply the analog of a force, which is like a force at an angle, right? Why won't it just turn immediately? Well, it won't if it has a really high sort of inertia. And that inertia, in the case of force, is just literally mass. But in other cases, like in rotating cases, it depends on where the mass is. If it's near the outside, you'll have to speed it up a lot faster, and so it'll sort of be a little harder. So that's the moment of inertia. So now I'll say if the sum of the torques is 0, then L is conserved, where this is angular momentum. Okay, we can write angular momentum as r cross p, where p is linear momentum. Now this might be not a good way to write it if p is constantly changing. So if something's moving in a circle, then p is constantly changing. The magnitude might not, but the vector would, right? And it might be a little hard. You also might want to write I omega. So that's, yeah, I guess that's it. Where omega here is it's the vector for the angular velocity. And remember that if something, let's say something's rotating like this, like it's rotating like this, what direction is the angular velocity vector going to be? So let's say it's rotating like this at some angle omega or some speed.
Out of the board.
Out of the board, right? Because we just take it's right hand. You use the right hand rule with the fingers, not these fingers, the 4 fingers, and you wrap them in the direction that it's going to go in this way, and so out of your thumb points out of the page, which is the angular velocity vector has a magnitude of just omega radians per second, and the direction is going to be out of the page. So we could draw it like this, I guess, or we could just write out of the page.
What's p?
P is the linear momentum. So, okay, so then I'll get to this. So this is for a rotating object where we have a moment of inertia and we have an angular velocity. R cross P, now in this case would be hard because first of all, we have a bunch of pieces of mass that are all rotating at different momenta and stuff. So that would be incredibly hard to use this for here. We'd actually have to do an integral. We'd end up getting the integral for I, but that's the whole, you'd never do that. But if R cross P is also true because every object, even if it's not moving in a circle, has an angular momentum. So if you have an object moving in a straight line with a momentum p, right? And let's say you just remember how when we do the torque problems, I said you could pick any point, and everything has some torque. Every force is equal to some torque around some point. And it's equal to different torques on different points, of course. So it's all dependent on the reference point, right? The forces don't depend on the reference point because we don't care. It depends on the object, I guess, but it doesn't depend on the reference. Torque and angular momentum both depend on reference points. So let's say we pick the reference point, let's say right on the line. So if I have some object moving with a momentum p just in a straight line, what's my angular momentum around this point? Well, I would have to use this r cross p. R is the distance from where the object is. Let's say it's like here. At this point or whatever, it's like actually. So I shouldn't write the whole path of the object. I should just draw the momentum. So it's the momentum vector. The object is here, and let's say I'm picking this point as my angular momentum point. R would be the distance between this point, the reference point, and where the object is, and P would be the momentum vector, the linear momentum vector. Now, of course, the way I've drawn it, they're parallel. R is here and P is here. Well, if I have two parallel vectors taking the cross product, I get 0, right? So in this case, my angular momentum around this point of this object is 0. And the way you can think of that is like, if I'm looking at this reference point, something's going near it, it can kind of spin something around that point. This sounds like a really silly way to describe it. This is actually kind of useful. If you imagine this is the reference point, just take a small disk around it. Put a little disk around it. Could this object ever spin this disk by like pushing on it? No, if it went right through it, of course it can't spin the disk because it's not going to spin. If it was a little bit to the side, then it could spin the disk, right? My reference point was here and the object was here, right? If I take a disk like this, of course, just make the disk a little bigger, I guess. Of course, it could just spin that disk. So this has a very high L, angular momentum, around this point, this object around this point. Okay.
That's the whole whatever.
Yes, because R would be here. P would be here, and so the actual angular momentum vector would go out of the board. Yeah, and then you could say out of the board, therefore it's going to spin something like this. Yeah, so it's the same thing. So and when you take an actual disk, a real disk, that really spins, every single point on there has some small angular momentum around the center. It's just that it's much easier to write things like this when you have a continuous big object. But technically this is true. Technically, technically you could write an equation that relates dl to, it would be complicated, I don't know. Something complicated. But the point is that if you do the integral, it becomes similar to this integral I. Yeah, anyway, it's complicated. But it becomes like a dm integral because you integrate over all the mass. But anyway, the point of this is just that we often use angular momentum for rotating problems and just using this essentially. But it's also, this is the definition actually, and it's true that every single object has some angular momentum with respect to some reference point, or it might be zero, but has some angular momentum, and we could find it with this. So, and we could see that by the problem with the person that's spinning in the chair. So, if someone's spinning in a chair and they pull their arms in, maybe it was on the homework, and they pull their arms in, we have to use the fact that angular momentum, because there's no just like in the previous problem, there's no external forces, momentum is conserved. So the same thing here, if there's no external torques, the angular momentum is conserved, right? So if you're spinning in a chair and with holding weights or whatever, and you pull them in, I'm just going to describe this qualitatively for start, and you pull your arms in, no external torques have occurred, right? Nothing extra, everything was in the system, right? So we know angular momentum is conserved. That means that before we had some I times omega, you're spinning at some speed omega. This is, I'll say initial. So this is L initial must be L final. I won't put the vectors because it's all in the same direction. So, and that must be I final, omega final. This is a little bit, well, okay. The point is that to change your omega, you know that your omega does change, right? When your speed does change when you pull your arms in. I mean, we know that from experiment basically, but therefore we can figure out that your I must change. And actually, of course, if you do the equation, if you actually say you're a cylinder like they want you to say in the problem, I think you're a cylinder. Okay, you have some whatever. They're going to be the same in both cases, so it doesn't really matter. But if you have some mass here and some mass here, right, the I of an object at some mass away is actually just m. This is L, ml squared. This is just this comes from the parallel axis theorem, which I'll talk about in a second. But anyway, it's just the parallel axis theorem for a single object with just at the origin, right? At the origin has no moment of inertia because it doesn't take anything to spin a point. But if you just move the origin away, you just have to add this. Anyway, I'll talk about that in a second with here. But this has this, and there's two of them, so it's this, right, plus your moment of inertia. When you pull your arms in, to L over 2, you get a new I that has L over 2 here. That's less, so you'll get a smaller I. So your I goes down, therefore your omega must go up, because they have to be constant, right? So this would give you that you go faster, which we know, of course, is true. The other one is if you drop them. The second one said if you drop them and let them go. Now, if you drop them, let's say you were spinning like this, they're going to go in straight lines like this, right? They still have they still have angular momentum like this. Now it's sort of linear because they're not moving in a circle anymore. But R is changing, but that's fine. It doesn't really matter. Their angular momentum is the same, and so if you wanted to write it like this, you'd have to write plus R cross P. This is a little complicated. You wouldn't really have to do a problem like this, probably. But you would want to say that your I is going to change, but your omega should be constant because some of the inertia went to the objects that are now going in straight lines. But they should have the same angular momentum as they did when they were moving in a circle. Anyway. That's okay. So, and actually, in this case, if we want to talk about,
if you drop them, you say your spinning speed doesn't change.
I don't believe it will. No. Well, we don't have to assume that because we can.
Because I depends on the mass, right?
I depends on the mass.
So if you're dropping the 10 kilograms,
yeah,
at least that would change, right? I mean
yes, yeah, because
a little bit.
So initially you'd have some big mass, so you'd have some this plus this, right? You'd have, I'll say for the disk it would be, if you have a mass m, we 1/2 m r squared if there's some radius r, right? So this is the total moment of inertia before with the objects. You're spinning at some speed like that. If you drop them, now your final moment of inertia is going to be 1/2 m r squared. That's it. You have some omega final. But then you'll also have to include some of the angular momentum went to the books that are now flying off. Yeah. So if you write them, this would be r times, and they're perpendicular, so we don't have to worry about the cross product. But the linear momentum would be mv. But remember, v is r omega. That's just true for things moving in a circle. The linear velocity here is the same as r times omega, where this is r. Right? So v I could replace with r omega. This is also big R. And you get, if there's two masses, it's 2 times this, and you get exactly this. Sorry, I used L here and R here, but this is the same as this. Don't worry about this too much. This was a very subtle thing. I'm just showing that this and this are the same thing. So that's a really good point. That if you're right, if you let go, your mass changes. How can this possibly change? It's because you have a new term now, because you still have to include the whole system.
The momentum that went away with
exactly.
Okay.
Because some of the momentum, basically, you lost some angular momentum, right? The system lost. The system didn't lose any, but you as a person did. So your I changes, but this doesn't necessarily change. We'd actually have to really plug it in to actually show this for sure. But then you could say some of it went into the things moving linearly, and plugging in this gives you that actual angular momentum.
So in that case, angular momentum is still conserved.
Yes. Because letting go of books is not an external torque. Pulling things in is also not an external torque. There's another subtle thing about all this, which is that when you have books, if you're spinning and then you pull them in and you speed up whatever, that actually costs. That's no torque because your force that you're using to pull them in is parallel to the R, right? So torque is R cross F, right? So if they're parallel, it has no torque. But keep in mind that energy, the work done to if you impose a force on some distance, the force you're pulling it in is the same direction as it's moving, and so there is some work that it takes to do that. So when you spin in a chair and you pull some books in, that actually takes some work, and therefore the energy of the system is actually not conserved, right? So that's a very subtle thing. If you're talking about a rotating system, you can talk about rotational kinetic. Remember, rotational kinetic energy was like 1/2 I omega squared, right? This is not conserved in this example, because some of the energy went into the work that you do to pull the books towards yourself. That's some. It's just like it's just like the inelastic collision. Some of the energy went into work to stick them together, to form them, whatever they have to do. So the same thing here. Pulling things in when you're spinning takes work. Anyway, I said this every time. So, okay. But angular momentum, of course, is always conserved. Okay, I was going to do a parallel axis theorem one. Is that good? Okay. So I'm not going to do the one I did. The one I did last time was the rod. So the rod, if you have a rod rotating around its end, it has a moment of inertia of like 1/3 ml squared, and if you have it rotating around its middle, it's 1/12. And you could go between those using the parallel axis theorem. So I won't do it again because you can see the video, but I'll do a different example, which is not as fun because we don't know the answer. But if you have a disk, so a disk rotating around its center has a radius r, a mass m, I center of mass. Well, sorry, I'll say I center because it's really I around the center is 1/2 mr squared, right? That's just from the table, whatever. Or you should, if you know one of them, you should know this one. It's also if you have well, okay, well, it doesn't matter. Okay, I'll say a hoop. So this is a disc, right? I can't, these,
Yeah, that's not what
none of these work very well. Disc, and then if you have a hoop, which is not a disc, a hoop, which is like you can stick your hand in it, like it's not, right? It's just like a, you know what I mean. Same with R in the same end. This actually has an I around the center of mr squared. Yeah. Oh, that was an N. Sorry. Anyway, this is like a filled-in disk kind of thing. So anyway, let's say what's the moment of inertia around this point? So what does that mean? That means that your disk is, instead of spinning around the center, it's actually going to spin like this. Like it's going to sort of revolve around this point. That's a weird thing to do, but who cares? So now we know that what we want to do is move the axis. The axis is here, like this. We want to move it to a parallel axis. I wonder what we're going to do with it. Well, we can just use the parallel axis theorem, which is I don't know, so let's say I, is I center of mass plus md squared. I'll say capital N, because that's this M. Where d is the distance we've moved the axis, right? And I center of mass is the moment inertia around the center of mass. It doesn't mean the moment inertia that we had before. So you can't just like use this and like move the axis a bunch of steps. That's not, doesn't work. You can't just add this when you move it a certain distance. It's specifically only works for the center of mass one. Now it just happens to be that the center of a disk is the center of mass, so we're good. But actually, yeah, so we're good. But if we had, let's say, a rod rotated around the end, we know is 1/3. This is L and mass M. This would be 1/3 ml squared. If we wanted to move it away, so it would be like a rod rotating like beyond its center, so it'd be like revolving around something. We cannot add md squared to this because this is not the center of mass one. Does that make sense? So we would have to use the 1/12 as the other one because that's the center of mass, right? Or if there was some weird mass distribution, you will never have a problem like that. But supposedly, there could be something with like a different mass distribution where like it's denser over here than over here. There's no, I shouldn't say that. You never, it's ridiculously hard. So, anyway, so then the center of mass here we know is 1/2 mr squared. And then we have to add m. Now, of course, d is the distance we're moving the axis. So, or in other words, you could say the distance between the axis and the center of mass. Right? Now, if I just move it to the edge of the disk, then of course this is just r squared. And so therefore we get 3/2 mr squared. And there we go, that's my I. And if I want to talk about things, if I want to say, oh, there's some torque and it's applied at the center, if there's some torque applied right here, this way, I'd say, some force applied there. Of course, that's not going to make it spin around the center, but if I said it's fixed here, whatever, it does have some torque around this point, but we could not use this formula to talk about the acceleration or anything like that because this is not the correct, it's not really moving around this axis, so you have to use this one, 3/2, right? So. Same thing if we had the same exact thing where we wanted to say a hoop rotating around the edge, which is like, if you take like a little, like a hoop and you do this, like a hula hoop, I guess, right? But like pretend that it's a hula hoop, but it's like around a stick or whatever, so it's not like changing its, because when you do it, I'm not going to pretend it. If you really did a hula hoop, it's changing because you're moving. I can't. Because you're moving, you're changing the actual center of rotation all the time. Because wherever it's contacting you at that point is going to be a new center, and it's going to anyway. So, so if we want to say a hula hoop, let's say around a point, so it would just be like going like this. Then we would do the same thing. We have mr squared. Now we want to, if that's the center of mass, is still in the center. And remember that it's important that this center is not actually in the, there's no mass there. So the center of mass doesn't have to be in the object. I don't know. That sort of, the first time you see it, it might be a little counterintuitive. But so we have I is I center of mass, which is mr squared plus md squared, where d is the distance we're moving. It's again r. So it'd be mr squared again, and we get 2mr squared. There you go. So this is for a hula hoop kind of thing, rotating around like a stick or whatever. Or if they just say hula hoop such that the the center of rotation is the same or whatever.
Do
Yeah.
this to find like the torque that's on the center. Like you have to look at it from a point other than or like are you looking at the torque on that point based off of force that's being pushed on the center?
I'm not saying, so we don't have to use torque. This is all true anyway,
Okay.
independent of torque. So if I call this a point, these are unbelievably bad. So if I call this a point beta,
Mm-hmm.
I like using Greek letters sometimes. If I call this a point beta, this is I around beta. So remember I said like with a rotational motion, there's a lot of choice you get because every object has some I around every point in the universe. Okay. If something's actually rotating around this point and there's some force here, you would need to use this to find the torque. Well, sorry, you could always find the torque. If something was actually rotating here, you would need to do this to find the angular acceleration, which again, angular acceleration also has a point. So if I say that, I can't, this is worst. Place it.
I don't know if those have been used at all.
I'll try this one. These ones don't really erase, which is why, other thing that I don't understand why they're here. Okay, oh, that's so t around a point, I'll say t around a point beta, sum of t around a point beta, is I around beta times alpha around beta. That's a little confusing, but you know what I mean.
Yeah.
So this is actually what they should say. Just like when we write F equals ma, it's really F in the, I kind of wrote it here, but F in the I direction is equal to A just in the I direction. It has nothing to do with the other ones.
Mm-hmm.
Torque around a point beta is equal to I around the point beta times A around that point beta.
So if they like specifically ask like around this point, this is when you have to use it.
Right, if they say it's fixed at this point. Now, if they say something's fixed at whatever point, then they say it's not moving, technically it's fixed at every point, right? Like, that's sort of, I guess that's sort of a philosophical question. But you know what I mean? If something's not moving, you can choose any point, because it's not rotating around any points. Just like if something's not accelerating, you can pick the force in any direction, the sum of them is 0. It doesn't even have to be, it can be diagonal, whatever. That's still 0. This is true if something's not rotating around anything. If it's static, you could pick any point, but you have to, well, if you pick any point, if it's not rotating, this is all 0, so it doesn't matter anyway. So the only reason you would ever really compute I is if something's actually moving, right? Because remember, if something's not moving, A is 0, and so you never need I anyway. So yeah, so thank you, I should have said that. You only really need to do this I calculation if something's actually rotating, and then you would do I around the point that it's rotating around, because otherwise you don't really have any answers. Because you could come up with some kind of formulas for things rotating around different points, and you would get you get weird answers. So if something they say it's rotating, it's fixed to this point, can rotate around this point, you would really need to compute I around that point to get alpha from the torques. Usually in these problems, it'll be also something can't rotate around more than one point. So if any object is rotating, it has to be rotating around a point, and then you kind of already have your answers. So like it ends up being less confusing when you do real problems than if you just think about it abstractly. Because again, if something's static, it's actually harder because you can pick any point. It's harder in the sense that you don't know which one to pick. It's easier in the sense that they're all true, but still some of the torques around any point is 0. So you can't really be wrong. You just might do something that's not helpful.
Something that confused me yesterday, when he was doing the torques summation, right?
Yeah.
With the poly.
Yeah.
How he determined the signs?
Yeah.
I mean, there was the T2 and T1, but I found it hard to which one was negative and which one was positive.
Yes.
He might have kind of mixed him up.
It was weird. He was like, okay, there's a minus here. And what?
So I was not paying attention to that, and so I don't know. But I sensed there was some controversy. Someone.
Yeah, I think for the one that was going down, I think one of the times he used the y direction like in this way positive,
Right.
and one time this way positive.
Yeah.
But I was also confused.
I'm not sure. Let's just. I'll make up one. So let's say it had some T2, T1. Now I'm not going to draw the other things. It is important that, well, okay, I'll draw the other things. I was about to say why it's not. I love giving explanations for why I'll do things and then not doing it.
Doing the opposite.
So if this is M2G, this is box 2. And this is really here, but I'm just going to. They're free body diagrams, so they're sort of in their own universe, right? T1, and I'll say, okay, it's just T1. Right, there's no other force. Let's just say there's no, well, okay, yeah, there's no friction. And this has some T2. And if everything's, now what's important though is that when you draw this, if they draw the situation with blocks and stuff, when they draw this, you're going to be very tempted to say that M2G must equal T2. Perfect, I can just plug in T2 is M2G. I don't need to worry about this tension. That is not true unless they specifically tell you that nothing's accelerating. Okay. In general, that's actually impossible. In this situation, that is completely impossible unless they say the pulley doesn't work, which they won't, because that would be really annoying. So in this problem, because there's only forces going, just forget about exact conventions of signs, but just imagine there's only forces going this way. Things are going, it's going to want to pull the rope this way, right? So there's only forces that way, and there's no other forces the other way. It has to move. It has to, well, no, it doesn't have, it's true it has to move, but it also has to accelerate, okay? That means that if this object is accelerating, the sum of the forces is T2 minus M2G. That must equal M2A, because that's units, right? So this is very easy to get confused to be like, I've seen many free body diagrams, they have ups and downs and they're equal. That is not true in this case. It actually is impossible for it to be true unless they say there's static friction or something. But they won't. That'll be really mean. So if there's no friction here, that means there's no forces going sort of to the left. This is one of your equations, okay? Now notice that I called this, okay, I'll keep the conventions. Notice that I called this way positive, up. But if I call up positive, actually, well, I don't want to change it because I know every time I say I'm going to.
He had wrote that the opposite way. He did mg minus t2.
Okay, you could do that, and then you'd have to use the same one up here, though.
Okay.
So meaning if you call down positive, you have to call to the right positive because it's a rope. It's connected. So in this case, remember, normally we can decouple them, and actually technically you could here too. You would have to just keep track of these tension. Anyway, it would be a little complicated. So I would treat it, because it's a rope and it's all connected, I would treat one way of the rope can go as positive and one way as negative. Okay, I don't want to change it because whenever I say I'm going to change something, everyone erases something and I feel really bad. So I'll call this way positive. And therefore this is positive too. Okay, again, it's not required that you do this. You could decouple them separately, but I think it's easier to treat the rope as a one-dimensional system. So therefore, the mass 1, this is mass 1, has, well, the sum of the forces is what? The sum of forces is just minus T1, right? And it must be equal to M1A, that's it. And notice I didn't use A2 and A1 because I could have, but then I know that there has to be equal because it's a rope. I can't, the acceleration has to be equal, right? So there we go.
Is there gravity on the top one?
Yes, so there's gravity and normal force,
okay.
But we're not gonna, right? So what I said about the direction of the rope, I'm treating the rope as the only dimension that I care about. Yeah, it is a little weird because I'm only talking about the y direction here. I'm only talking about the x direction here. So it seems like confusing. But I'm basically talking about the rope direction. So that's what I care about because that would give me the other one wouldn't give me any information useful. So, and now of course, so now we have these. Now we have how many unknowns? 1, 2, 3. That's silly. We can't have that. We do have now we could use, like I said, I think I said like an hour and a half ago, that we could talk about the sum of the forces on the pulley. But it's not going to be interesting because we're going to introduce a new unknown, which is the normal force at the center, and that's not going to be very interesting. Well, sorry, it might be interesting, but it won't be, it'll give us a new unknown, and we can't possibly, if we have 3 unknowns already, our last equation must have no new unknowns because otherwise we can't solve it. So let's talk about, of course, the last thing would be, let's say this is a mass big M and a radius r, and it's a disk, let's say. Now we want to talk about how the sum of the torques on this is going to be I alpha, right? And so the sum of the torques is going to be, well, there's one torque going, and I'll call this negative because it wants to, I'll call this positive because it wants to pull things in this direction of T1R. That's positive because it goes in the sort of same direction as that. Minus, and it's just this other one, T2R. How did I know it was T2R? Because the force is T2, and it's applied at a distance R, and because they're perpendicular, everything with pulleys is always going to be perpendicular, because whenever you have a rope anywhere off a pulley, it has to be perpendicular to where it leaves the pulley. Like, that's how lines work. Anyway, so we don't have to worry about the sine theta, whatever. That's the sum. Now, there's no more torques, right? There's gravity and all this stuff, but again, that's at the center. It doesn't exert torques around it, so that's it. This must be I, which is 1/2 m r squared times alpha. Oh, look what we did. We have a new unknown. It's a weird thing to say. I sound like a kindergarten teacher. No, we have a new unknown, which is alpha. Exactly, when you use A over R. The reason is because it's very important that it doesn't slip. Now, if it slips, it would be really hard. Again, these are going to be... There's all these things that could happen in real life, and so I want to address them so that you know that we're not forgetting about them. But if, like, the rope was, like, slipping and kind of friction was pulling the pulley, that would be a hard problem, and then we wouldn't say this. So rolling without slipping or whenever things are rotating, just like the tangential sort of acceleration or whatever, or position, basically when things are 1-to-1 between rotating and linear. That's how I should say it. Things are 1-to-1 between rotating and linear. When you pull the rope, thing turns. When you pull it back, the thing turns again. That is the condition to say that R alpha is A, or R theta is X, or R omega is V. Yeah. And the thing I said to somebody, maybe you, I don't remember who, that it's very easy to not remember where the R goes. So the way I remember it, I promise I actually still remember it like this, is that the R goes with the Greek letter. Again, it sounds like a kindergarten teacher thing. But, and so, of course, often you'll use the other one where you divide it, but just the R is multiplied by the Greek letter, because then anyway. Technically, you could use dimensional analysis. Yeah, that'd be the fancy way to do it, because this has units of meters per something. This is meters, and this has, but you know, it's very easy to just go with the Greek letter. And so alpha becomes A over R. Now we have, this equation has no new unknowns. That's excellent. So this is A, that's A. Those are all the same A's. One of these cancels, and this is a thing that happens a lot too, is that all the R's cancel. If we divide everything by R, we get that. Now this looks a lot like a force problem, and it kind of is. Well, actually, don't think of it like that. Now that it is kind of like a force problem, because it seems like, oh, well, we just have a force that way and a force this way. It's like a one-dimensional force problem, right? But it's a little bit weird because this is not M, this is like an effective mass. Kind of like effectively it has half of the, anyway, now it doesn't make sense anymore. So just don't, it's just an equation. So now we have this, we can just plug in. I don't want to do the whole thing, but, well, I could do the whole thing. Actually, let's do the whole thing. That would be kind of cool.
But before, can I ask, I'm going to add something that I saw in the homework that kind of annoyed me. Mm-hmm. In the homework, they say that you have an axis that has friction on top of that, like I don't know, a little circle.
Oh,
an axis
yeah.
that, what I thought is, okay, this friction force must be opposing the direction of the motion.
Yeah.
So that's the way you will get the torque.
Yes.
Like, okay, there's a F that it's in the opposite direction to T2, for example, that has some magnitude.
Yes.
You know
Yeah.
what I mean?
Mhm.
Yeah.
Yeah. So if you had friction here, what that would mean is that you.
But with a radius, it's like an axis.
Oh,
It's
yeah. I was gonna
inside
say
this.
that's yeah.
So
So it'd be like
something like that.
yeah. So if you
Because
had
there's friction everywhere there, so it's
exactly. Well. So I would say if you had that, you would first have to know which direction it's moving.
Okay.
You'd have to know that the whole thing is going this way, right? And it has to because there's only forces going to the right. There's no forces going to the left. So if you just had two, like if they had a problem with two masses hanging and you didn't know which one was heavier, you actually couldn't do that problem because you wouldn't know. There's actually a example problem that it's like two ramps. I haven't seen any in the book or anything, but this is a very common physics problem where you have a block, another block, and there's friction on both of these, and now it's going to slide one way or the other, and they say, find, I don't know, whatever. You actually can't do this right away unless you know one of them's heavier than the other. If let's say they're at the same angle, because you don't know which way it's going to slide, and that actually changes the direction of friction, right? Gravity and all that stuff doesn't matter. It doesn't, it'll just be negative. It's fine. But you actually can't do it unless you know which way it's going to go. This case, we know that it's going to go to the right. So, so in that case, we would have to compute, the force of friction times the small radius or whatever, right, would be, and of course it's applied at right angles always, you assume that. And that would be some torque. And of course, if it goes this way, that would be some torque in this direction. And so when we compute the sum of the torques, we would get this minus this. And of course, if it goes this way, the torque would oppose the motion, so it would be in the same direction as T1. And so you'd get that torque due to friction. I'm not. It would be like F times R, right, or little r. I don't want to make new variables, but yeah, you would add it in the same direction, just like to the sum of the torques, same direction as as this one because it goes
It's
the same way.
opposing the motion.
Yes, exactly. So that's how you do it if there was some friction. In other words, they couldn't just tell you that there's friction in the point that it's applied at because that doesn't have how do you calculate the torque? The whole radius seems to be 0. So they would need to tell you that it has some, like if you hang something on like a rod like this, the friction is actually applied on the edge. So you just sort of need the radius. Anyway, this is all engineering stuff. But anyway, so that's how you just add it. And so remember, when you're adding, just like when you're adding forces, choose one direction as positive, one negative. In this case, we're choosing one sort of rotational direction as positive, and this is negative. And it's much easier to keep everything in line when you choose sort of this, this plus, and this plus all sort of match. Again, it works if you don't, but you have to sort of keep track of the signs a little bit better. Anyway, now that we have T1 is minus MA. So I'm plugging in this equation here. I'm just kind of doing this a little fast just so I can get to the answer because I just want to do some stuff with the answer. And this T2 is minus, and then T2 is M2G plus M2A equals 1/2 MA. So I filled in this equation with the two tensions, right? Hope I did it right. That's fine. I guess I kind of did the same problem a while ago, but well, actually, it's similar to I did one, and it's on the video somewhere, of two blocks hanging. This is slightly different because there's not gravity from one of them, but otherwise it's kind of the same. And I have minus M1 minus M2 A minus M. Oh, sorry. Oh, that's right. Minus M2G equals 1/2 MA. And now I want to put, I'll put all the A's over here, I guess. So minus M2G 1/2 M plus M1 plus M2 all times A. And then I'll write the answer up here. I hope this is right. Actually, it is right. Minus M2G over so as usual, you could do some analysis, not dimensional analysis. Oh, you could do dimensional analysis, but you could do some limits to make sure this is right. What happens when M1 goes to 0? M1 was the block up here. If M1 goes to 0, it should be just like a block on a pulley that's just sort of falling. It's not going to fall free fall because it has to spin the pulley. Well, if we knew what that formula looked like, if we covered this up, that actually is exactly what it looks like. So if we've done that before, we would know. That's exactly right. What if M2 went to 0? If M2 went to 0, what should happen? Well, that's just like if this wasn't there, well, it's just a block sitting connected to a pulley. Nothing's going to happen. There's no forces. So if M2 is 0, we get 0. That's not, so A is 0, I should say. So that's good. What if the mass of the pulley went to 0? If the mass of the pulley went to 0, that should be like you have some force of gravity that's M2g, and it's sort of pulling an extra weight with it that doesn't contribute to gravity. So that should be like M2g over M1 plus M2. So if we set the pulley mass to 0, we get exactly that, minus M2g over M1 plus M2. So in other words, it would be like a force problem where you have some mass pulling a bunch of more mass than itself. If, this is going a little overboard now, but if the pulley and the other mass went to 0, it should just be like a thing falling. So it would fall at g. Well, if these two went to 0, we'd get minus M2 over M2. That would just be minus g. So that's literally all the possible. No, it's not quite all. Actually, yeah. So that's actually all the possible situations. Does that make sense?
Mm-hmm.
So you don't have to do all those things, and we could check the dimensions too. That would be a sort of easier check, especially on a test. You should always check the dimensions. We see that masses on the bottom all cancel with this mass. We just get units of g. So, but yeah. So this looks a lot like a force. Well, it looks kind of like a force problem. I guess we don't really see force problems like this, but essentially you just get these three equations because we have three objects. We get three equations, and they're related by the fact that their accelerations are all the same. And there's only two chords connecting them, tensions connecting them. So we know we have to get three unknowns total. And luckily we have three objects, and it's, well, yeah, so. Is there any question about this? All right, what else? Well, if you think of anything.
Well, I was having a big headache with the last one with the rod.
Oh, that one was terrible.
It's like, could I change the origin of would that work? I mean, what's the strategy to solve
the origin for what?
Because I feel like it would be easier if it's not in 3D. You know?
Yes.
But
So
how do you deal with that? I don't know. Because the tension is coming to the front, right? I mean, that rope.
Yeah, so it doesn't really make sense because there would have to be. So actually, there was some video. I put it up. I talked about that problem for a while, but it was the last. Okay, yeah. So that I'll say the summary of why that's impossible, which is that yes, you could talk about the forces being zero. I talked about why there must be a force up here, but if you just had gravity here and you had some tension here, it's not a straight line, but wait. And let's say you had some force applied right at where it pivots.
Yeah.
The torque due to this one and the torque due to this one, there might be different because they might be at different angles in 3D.
Yeah.
But they're gonna if you just look at like the projection here, they're going to make it rotate this way at some. So in some plane, there's going to be some torque going this way.
Yep.
Therefore, you need, because it's not moving, unless it's literally falling on the ground, you must have some torque going up this way, right?
Opposing that.
Yeah, and you can't have any torque from this point because, like, there are zero. Like, no force here is going to apply a torque. So what you really need is force to be applied slightly away. So in other words, it's like holding up like a rod or whatever. I can't just hold it by one point. I need to like apply some leverage away from that point.
Yeah.
Otherwise, it's impossible. If I just literally hold it by like one point, it will fall
rotate.
because there's gravity. And now that's not even including this, but just so the way the system is drawn is first of all is impossible, but it's possible if they didn't tell you something like there was some small distance between where the normal force is applied and where it can pivot or something. But they don't say anything about that, so there's sort of not enough information in that problem. You could totally do everything but the forces. There's no impediment to doing anything but the forces. I don't know. You could say something about the torques. Just say something about the torques. Doesn't really. Find some torque. You know what? I don't care too much about the. I'm not going to look at like all the vectors and make sure all the. Just if you say something about the torques, you'll be fine. Because again, it's impossible. It's impossible with the information they give you to actually compute all of the torques and forces.
Well, yeah, I imagine what you're saying is right because it's the joint there is a screw, right?
Yeah.
So the screw will have forces in different distances.
And specifically, if it has some length, like it's takes up some space, it will apply some force ahead of like the edge, right? It can't. Anyway, you see what I mean? Like
I know what you mean.
So the way they've drawn it it's possible if there's stuff they're not telling you, but then why do they want you to find all the torque? So it would make a lot more sense if they said it was just connected to a pivot and with no force, well, with maybe some normal forces, but then the rope was like holding it up. That would make way more sense if you had like a rod that had gravity, but then there was also like a chain holding it to like the wall, right? And so it was like sort of leaning, like hanging from the wall, right? That's like the problem. This is also in one of the videos. I think it's the one before last or something, where I do the problem with the rod that has a mass and there's a thing hanging from it, right? Were you? I don't know. Maybe you were.
Like two of them, I think. You've done them in like two separate.
Oh, okay. You'll find them.
Where are they?
All over the place. Oh, they're on YouTube.
On YouTube. Oh, okay.
If you go on the Slack channel.
Oh, okay.
Yeah.
Perfect.
I think you
pinned
did it on,
them.
like, Saturday and Wednesday.
Yes. Then if you have a rope here, T, right? You have some mass here, some mass here. This problem makes a lot more sense because there is some normal force here and some friction force going up, but it's a little hard to figure out. But you can use all the information to solve for all the torques and all that stuff. This one sort of doesn't, even intuitively, it seems really weird. Like, I don't sort of understand why would you want to, anyway, it doesn't really make any sense. So, I don't really like this one.
Well, why would you want to pull from that?
Why would you want to hold it down? It's already, it's ways, like, anyway, it doesn't really make any sense. So,
what I thought is, okay, this guy wants to break the joint or something.
Yeah, it looks like you're trying to break it.
I'm trying to break it.
Yeah.
I don't know.
Anyway. Good. All right.
Thank you.
So yeah, so this one will be on YouTube. Yeah, so if you go on the Slack channel and you go on pinned things, I think I tried to make a playlist. I don't remember if I actually did it or if I tried and then didn't. Anyway, it's not very hard. Anyway, I'll do it. Everything. If you go on just videos on my channel, like they're public now.
Thank you.
So you could see all of my videos, and it'll have I just have office hours, and then there's one of the MATLAB reviews is recorded too.
Okay.
That's good to know.
Sorry, I guess this is not the right time to
Say
tell you.
thanks for that.
But
I've been stressed out beyond belief, and you tell me now.
oh, of course, no, the answer's wrong. No, yeah, sorry. Well, anyway, I don't think it's a very good quality video.
You can see clearly.
You can?
You can.
You can't. Okay.
You can.
Well, so you didn't miss anything.
All right, well, good. Probably would have stressed me out more. I'm like, you
Yeah.
can't even see the answers.